Welcome back, everybody. The plan for this week is to give you a quick review of some of the gates which are interesting for the solution of the project, and also for the exercises which we have this week. And at the end of the Jupyter notebook, which you see in front of you here, there are exercises which Karen has developed for the bell states. And this is going to be our first example, which we will also discuss in the project. Now, in the Jupyter notebook, or the slides for this week, you will find examples on how you can run this with a popular tool which is called Qiskit, which has been developed by IBM and is an interface to the IBM machines. So I will just give you a quick and rough overview on how you can perform the calculations on the bell states, which will also be part of the project. And as part of the project, what we would recommend is that you start thinking of, and this is one of the meaning behind the session today, is that you actually start thinking on how you will write your own code for acting on the bell states, and later on the typical Hamiltonians which we have listed in the project. So you will see that the first Hamiltonians which we will encounter in the project, and if you go to the website of the course, the GitHub address, and you click on doc here, and you scroll down, you go to projects, and you will click on project 1, and then you can move on, and you will find the PDF file here, which was also sent to you electronically. And you will then see that the first part actually deals with you applying the Hadamard and some other gates and the C0 gate on the bell states. So here you can compare your codes with the results obtained with Qiskit, and these are the codes which you will find in the slides here. Then when you're done with that, I mean, setting up the basic states, comparing with Qiskit, which is a very useful thing to do, then we are going to look at the two Hamiltonians which we have been discussing in the lectures. And these are Hamiltonians which we will rewrite in terms of Pauli Z and Pauli X matrices. And when you've done that, then we can actually, we can solve these equations numerically with standard eigenvalue solvers. And when you're done with that, we can then move over and actually simulate that with something which is called the variational quantum eigensolver. So today, we are going to have our first encounter of how we can construct gates. And then when we have the gates, how we can make measurements and extract information from such a measurement. And this is something you will have to do writing your own code. And when we then are implementing these Hamiltonians, and this is something which we will discuss in more detail next week. So the topic next week is us moving away from the Hadamard and the C0 gate and actually constructing a circuit for simulating these simple Hamiltonians, which you see in exercise B, which is this Hamiltonian here, which we can easily diagonalize by hand. I mean, it's a 2x2 matrix. So this is not a big task, it's just a second order function we have to find the roots of. And then we want next week to discuss both how we can simulate this ourselves and how we can implement an algorithm which is called the quantum eigensolver. So that will be part C, so which we will continue discussing next week. And then we will extend that simple Hamiltonian to another Hamiltonian, which we met in the lectures last week, which gave us this 2-qubit system where we have these computational basis states, and we end up with a 4x4 matrix which we have to diagonalize. So obviously, this is again a walk in the park for a standard eigenvalue solver. It's easy to diagonalize, but we're also going to see how we can set up the different gates and circuits for simulating this system. And these are things which we will discuss now in the next weeks in connection with both us setting up the simulation tools and also discussing this variational quantum eigensolver as algorithm. So that's going to be the kind of road or the path which we're going to take. Now, in connection with this, and this is something which I was not aware of, that IBM has actually made available the 127 qubit machine. So what we have here are some simple instructions on how you can get an account and actually make runs on the IBM machines. And I wanted just to guide your eyes towards that first, because it's something which I recommend doing. And I didn't know that IBM 127 qubit machine was available. I thought it was only the smaller ones. So the Bell state simulations, which you find below after Karen's exercises, is a simulation which I was running during this weekend. And you can follow that one and just see how you can compare the code you will develop with IBM's Qiskit and running on the IBM machines. So the instructions is just go to the quantumibm.com, and then you just create an account and follow the instructions. Now, one thing which you will need is to have your own token. And I will show you where you can fetch that when you go to the your account page on ibm.com. But I wanted to show you, if we now scroll down to the very end of the slides this week. So I'm just going to go down here. And you will find after the exercises which Karen has set up, what you will find then is this header, testing the Bell states. The first code which you find here is actually us setting up a circuit with 2 qubits, and you would define it like this. And then you apply the Hadamard gate to the first qubit, and this is indicated with 0. And then last week we discussed, and you will find this information in the lecture slides as well, we implement the control NOT gate, where the lower block to down in the matrix, and you will see the matrix again just in some few moments, is given by a Pauli X matrix. So this is normally the C0 is normally called a CX gate. And this is the CX gate, where the first qubit is normally called the control bit, the control qubit, and the second one, which is this marked here, is then given by the target qubit. So the typical circuit which you will set up then when you visualize it, and this is something which you should think of setting up yourself, start with just 1 qubit and acting with a Hadamard gate. This is one of these fundamental gates. This entangles a state. It's not entangles, but it sets up a linear combination of qubit 0 and qubit 1. Then the X here is a Pauli X gate, and then you see this dot here. So this is actually a C0 gate, the one which you see here. So what you will see is that these simulations are normally set up in terms of circuits and gates, as if you were to set up an electronic circuit. So M here is a measurement on the first qubit, and M here is a measurement on the second qubit. And we actually want you to write a code which does this, because when we move on to these simpler Hamiltonians, we're actually simply going to extend what you see here. Now, when you're running the calculations, you would run this many times. So I've run it 10,000 times, and I am setting up a linear combination. So let me just switch to the whiteboard here, just a moment. So we can do that. So if you look at the Hadamard gate, which we are setting up, this is a gate which acts on 1 qubit. And you would typically see this written in terms of an H here for Hadamard. And this is given by the following matrix of 1, 1, 1, minus 1. So suppose now that you have a state psi here, which is a superposition of qubit 0. So this is a 1 qubit operation which we're going to perform. So it has a qubit 0 multiplied with a factor or coefficient alpha 1, and then we have qubit 1 here. So when the Hadamard gate, or this matrix, being multiplied with this state here, then what we get is simply a operation which is given by 1, 2 of 1, 1, 1 minus 1. And this is obviously multiplied by alpha 0 and alpha 1. And when we write it out then, what we are going to get is an alpha 0 divided by square root of 2. And then I have 0 plus 1. And then we have plus alpha 1 divided by square root of 2. And then I have 0 and minus 1. So we still have a state which is now given as a linear combination of qubit 0 and qubit 1. If I act with this Hadamard gate on just qubit 0, then that simply gives me a state which is now a superposition of 0 plus 1. So we produce a linear superposition of the two states. If I act with the Hadamard gate on the qubit 1 state, so I'm just calling this qubit 0 and qubit 1 in a kind of sloppy language. And this gives us simply qubit 0 minus qubit 1 here. So these are simple operations actually to perform. And it's something which we want you to get started with. There are some other interesting operations here which you should also consider. And this is given by the Pauli X and the Pauli Z and the Pauli Y gates. So we would typically write a Pauli X gate in terms of an uppercase X. And we know that this one is 0, 1, 0. We have another famous gate, which is sigma Z, which we would typically write as a Z here. And that is given by 1, 0, 0, minus 1. And then we have the Pauli Y gate, which is Y, and that is given by the letter Y here, and that is given by 0 of I, and then I have I, and it's minus I, 0, and 0 here. So this is the Pauli Y gate, and there are some interesting relations here which we are going to need later, and we will discuss that in more detail next week. So we can actually show that the Pauli Z gate is given by a Hadamard gate times a Pauli X gate times a Hadamard gate. So just try this and see if you find the same relations. And I have the same with this one, which can then be written as minus Y. And this is also written as X times Y times X. This becomes important, these relations are important when we are rewriting the Hamiltonian in terms of Pauli C gates. And the reason for why we want the Pauli Z gates is that these gates have qubit 0 and qubit 1 as eigenvectors and eigenstates. So what we have then is, if I do this operation here, this is the same as a Pauli X gate. And we also have that X times Z is equal to I times Y. So these are some mathematical relations which are very useful. So the Pauli X gate flips the components of a qubit. So if I act with the Pauli X gate on qubit 0, that flips it to qubit 1, which is easy to see. And if I act on it with the qubit 1, that flips it to qubit 0. Now, the other gate which we would see in connection with the Bell state is this C0 or CX gate. And I'm going to set them up in the slide, just briefly discuss them in the slides here. But the thing is that when you look at these operations, they are typically rewritten in a graphical form as circuits. So you can now think of you having a qubit 0, which comes in. And then if you act on that with a Pauli X gate, you would write this as a circuit. And then this gives us, then since it flips the qubits, it gives us a qubit 1. So this would be a typical way to graphically represent this operation here. When you look at the operation of the Hadamard gate, you would then, obviously, you would rewrite it in terms of, suppose now your initial state is a qubit 0. You write it with an H here, and that gives you a superposition of the two states. So you would have 1 over square root of 2, and then you have 0 plus 1 here. So that gives you a superposition of the two qubit states. So sometimes you suppress the initial and final states, and you just write a circuit in terms of gates. So you could now think of acting on two qubits with a Hadamard gate, where you act on the Hadamard gate with the first qubit. So like the exercise on the Bell states is a system with two qubits, and you can leave the entry point unspecified if you just want to write the circuit. So this would typically be given by you operating on the first qubit with a Hadamard gate. Nothing happens with the second qubit, and then you could apply other types of gates. But what we are going to do now is to apply a C0 gate. So mathematically, and the way you will be programming this is nothing but a series of matrix vector multiplications. But we depict it graphically in this specific way here. So this would now given by a CX gate, where we have a target qubit, which is the first one, and then we have the a control qubit, and then we have a target qubit. Then you can keep doing operations which, translated into a mathematical language, are nothing but matrix vector or matrix multiplications. So the first one here would typically, suppose now we have a qubit 0, and we have a qubit 0 here as well. So this will be an initial state, which is 0, 0. So the Hadamard operation acts only on the first qubit. Then we have a C0 gate, which can do something depending on the value of the states which we have, and it can flip the target qubit, or it can just leave it unaffected by the operation. Then we can continue, and we can perform a measurement on the first qubit, or we can have further operations. So we can have a sigma x, we can continue like this, we can have a sigma y, etc., etc. So these are series of operations which we can perform, and that defines a circuit. So this is something which has established itself as a way to represent the different mathematical operations which we are performing. So next week, we will look into more details how we can simulate this quantum mechanical system, which is given by a 2x2 matrix or a 4x4 matrix. And we are rewriting the Hamiltonian in terms of the sigma x and sigma y matrices, the sigma c matrices. And then we are going to rewrite those as mathematical operations in terms of matrix vector multiplications, which we will depict graphically in terms of circuits. So this is a kind of demystification of what these circuits actually mean. So read this as a series of matrix vector and matrix multiplications. So let's go back to the Jupyter notebook for this week. And so you can see now that we are going to perform a measurement on qubit 0, and then we perform a measurement on qubit 1, and we want to figure out in which states they are. So these are just ways to set this up in using Qiskit, and I recommend actually to take a look at the instructions, and you can see now that in principle, since we now have a state, we are looking at the Bell state phi plus, which we defined last week, where we have a linear superposition of the state 0, 0 and 1, 1. So that means that if I perform measurements, I should find, since I run 10,000 measurements, I should then find 5,000, ideally 5,000 0, 0 states and 5,000 1, 1 states. Because remember, there is a factor of 1 over square root of 2 in the definition of the Bell states. And if you go back to the definition which we have up here, the Bell states are defined like this. So we are going to look at this state which you see here. And this is the kind of exercises which Karen has set up, and which we are going to go through during the hands-on session for the rest of the lecture today. So the phi plus here you see now you should get, when you square it, this should give you 1/2. So that means that if you run 10,000 experiments, as you've seen here, then you should actually ideally get 5,000 and 5,000, but you don't get that exactly. But what you see now, when you plot it, there is no admixture of a 1-0 or 0-1 state. However, when you simulate this with the, so there's one package here, and this is what I wanted to give you. This is actually my token. You need to plug in your own API token here. And then you're going to set up the way you're going to run the calculation. So we are going to have the hub, which is the IBM queue. The group is open, project main, and I'm running on this machine, which is called IBM Osaka. And this machine has, so the first calculation here is actually one which runs quickly, because this is a simulation which doesn't involve calling the quantum computer, but it actually performs a model with a noise model. This is something we will come back to later. And then this is the same circuit, 10,000 shots. And then you will see that there is a weak admixture of the unwanted states. So 0-1 and 1-0. If I now run this on the actual machine, so the final part here is actually me running on the IBM machine here. And if you do that, what you will find, this is actually still running, as you can see. So I submitted a new job, but I can go back. So now my job is queued. So there are many people running on it. But if I go back to the way you should set up your account, so let's just do that. And I need to find my window here. Here we are. So if we do that, and go to the IBM machine, you will now see it lists the set of jobs. And you will see that my job on IBM Osaka has been queued, and my queue position is 16. And that has to do with the fact that I'm not paying. If you have an account, a research account, where your institution pays for it, then you move quickly in the queue. So this was queued roughly an hour ago. But you can look at the jobs which I completed like yesterday. And if I look at that one, there is a summary of the job which I run. And you can now see when it was created, how many where I run it, the number of shots which I did, the number of experiments. And then you can see the distribution or the frequency of the states. And you can see now that of this number of shots here, 485 00. I have 484 with 1-1, but I have a mixture of the unwanted states. And this is something which, in a way, you have to live with. And this leads to all discussions about noise and noise corrections, etc., which we will just leave out now, just for the moment. So when you're running your own simulations, this will never happen. It sets also up the circuit which I've been simulating. So I have a RC gate, I perform the C0, the CX gate, etc., etc. Now, when you're setting up your account, there is an icon up here, which is the account one. And this in the account piece, one of the things you need then is a token. So you saw that I had this API token, which I had pasted in. This is the one you have to click and just copy that and paste it in to the Jupyter notebook, which you have available. And then you can then run this with your own user account and access the machine which are available. So you can look at compute resources, and you can then see the machines which you can actually access. And this is something which is pretty new. So you can really make runs on different machines here. And you see that the 127 qubit machines have been made available. And you also have a 63. This can change. Every time I check this, I will see some other different machines which pop up. But take a look at it, and I recommend actually this, running the calculations, you writing your own code, and then running this on the IBM machines as well. Okay, what I want to do now is just quickly go back, and then we are going to terminate this session, and we will have just the hands-on part. So let's go back to the Jupyter notebook for this week. So as I said, the thing which we are going to look at now, when you look at the exercises, these are the exercises which Karen has developed. And before that, there is a discussion of different types of gates and how you can implement this with Qiskit. And the thing I wanted just to draw your attention to is one of the gates which we need to look at. And we will discuss many of these circuits and how we build them up gradually through the next weeks in connection with the work on the project as well. So many of the lectures which you will see coming now before the Easter break, they will be geared towards us studying the project and linking theory up to the way we solve the exercises in the project. So the first exercise, or the first part of the project, part A, deals with the bell states, and this is what we have prepared for the hands-on session today. And these are things which are much better to actually sit down and work on, either in groups during the session. So in the weeks which come, we will also split the lectures a little bit in just a plain lecture and then the hands-on sessions. So the C0 gate, which we are going to use, which is also called a CX gate, because you will see that this lower block here is a Pauli X matrix. So this has the property that if you think of the first qubit here as the control bit and the second as a target bit, when you act on the state 0, 0, it doesn't do anything. When you act on 1, 0, it flips. So if this qubit in the control qubit is a qubit 1, then it flips the other qubit. If it's acts on 0, 1, nothing happens. If you have 1, 1, it changes to 1, 0. And this is the type of operation which we will do together with a measurement. So these elements are what you need today. And I would recommend that in addition to running with Qiskit, that you start actually looking at how you can write a code for setting up the states and then performing these operations. And remember now that the gates and the circuits which you define, they are translated into a computer program, just a series of matrix vector, 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 matrix, matrix multiplications.